In this lesson, before we go on to get more information on how to run projects in SpectraCyber, let's take a quick look at some of the tools that are provided for your purpose of being able to make decisions on how you want to collect your data. Under the Tools section here, there is the Manager, which is for adding and modifying changes into the database table. We use this database here of radio objects in project mode. They're not normally used in the user mode, which I'll explain later in a future lesson. But here you will find a listing of all of the different objects. You can browse forward through these objects here to see which ones you may want to work on. In some cases, it gives all the information, including flux density on it. We can add new objects up here. Your catalog number can be anything generic text. It doesn't necessarily have to be a catalog number, which you can see we have different values over here. The object name, give it a name that makes some sense to you. Typically, I'm giving it code names here that people know about, or it could be a name of a particular object in the sky, like an M33 or whatever you want. The flux density, if it's known, should be added in. What is important, however, is to put in a valid right ascension and declination for the object. You can do that by either entering data directly into these boxes, clicking in the box, or you can use the up-down arrows. It will check to see that you are getting valid information. You should not be out of range. Here you are going to insert into the box directly, and it should be a decimal number. The object types are over here. There's several of them predefined. You can scroll through these and you can pick the ones that you want. Of course, if you don't know it or you want to just use the other to identify different objects, you're available to do that. And when done, you can save it. You can delete something here. Say you enter something wrong. But be a little careful with deleting from this table, because if someone has already run a project mode, that project's going to assume that this data is in the table. If it's not found in the table, you will upset the projects that are being stored underneath this particular object, since it will not be found. So be very careful about deleting, but modifying and changing something because it was entered wrong and incorrectly is perfectly okay. You can then go ahead and make the changes on it. You can select any of these objects you want by clicking on the button on the end. And now we've picked this object up. You can then modify the table if you wish to fix anything or delete, of course. And just be careful. I'm going to cancel so we don't change anything here. Another interesting tool is a very simple one called the Antenna Designer. If you're new to radio astronomy and you're designing and building your own antenna, this is a simple, helpful tool. You can put in the parameters for the shape of the antenna and the wavelength you're going to be using on. This is at 1420 megahertz, or the 21 centimeter line. And using these default values here, let's just get a quick calculation, and you'll see that it'll tell us where your focal length is, so you can properly design your antenna feed elements. It gives you an idea what your gain is going to be like, and what the beam width will be for that particular diameter. So this is just to help you prepare to design an antenna if you don't have one of your own and you need to build one. The last tool here is particularly interesting. Here's where SpectraCyber separates itself from most other programs that acquire data on a SpectraCyber. The SpectraCyber program has a built-in Doppler correction velocity calculations. These are done to correct for Doppler shifts that could be that are caused by the Earth's revolution around the sun and its rotation. In most cases, you may be doing a meridian transit. That meridian transit will have a radial vector pointing directly perpendicular off of your line of sight, and the Earth's rotation would be 0 at that point, since its horizontal vector is dropped to 0. So you will not be getting any effect from the rotation of the Earth. However, the revolution of the Earth about the Sun will be affected depending on where we are in the Earth's orbit about the Sun. So those correction values are printed out for you. This is a very detailed calculation, and it comes from calculations originally in a Fortran program way back from the 1970s. It has been converted and updated to today, and all of your data is going to be based on the catalog of JD of EPIC 2000. So over in your when you're entering your data for your object in the database that we just looked at, be sure that you're putting in coordinates based on JD 2000, the EPIC year of 2000, because it will calculate all of those radial motions and update to the proper right ascension and declination for the current time. Now, let's just do a quick calculation here just to see how this goes. You notice that the right ascension and declination are set for 0 hours and right ascension and 0 hours declination. This is just a sample. Of course, if you put in a right ascension and declination here, you can then predict from down below when this object will be crossing your meridian and when you should be ready to go ahead and observe the object, and at what altitude and azimuth position you need to place your antenna in if you wish to move your antenna toward that direction if you're not going to be always on your meridian and doing meridian drifts. Here we see that the object has been precessed ever so slightly to bring it up to current date for this epoch of this year, and these would be the new coordinates for it, very slightly changed. This is the portion here where we get the heliocentric corrections. This is the time and date at the center of the Sun, not the Earth's geocentric time, but the heliocentric time, where most of these calculations would be based upon. And here's your observed distance from the Sun. It gives you distance in meters from the Sun. The rotational velocity of the Earth is given here in kilometers per second. It's just interesting information for you, but the most important stuff is down here in these things. This is where the heliocentric velocity is. This is the Doppler shift caused by the Earth's revolution about the Sun. And this term can be added to, in this case it'll subtract, but if you add it to the Doppler shift that you measure from an actual scan of some object, this will remove this interfering Doppler shift caused by the Sun, and you'll be getting the true Doppler shift that is caused by the object itself. And you can also use the barocentric position, which happens to be the barocentric point. It's the gravitational balance point between the Earth and the Moon, and you can use the time from there if you wish. And then this is the binaural time. These are the correction factors that normally are applied and will be put out in a spreadsheet program if you output the data through the export commands. You're up to using these as you wish in any way, but the calculations have already been performed for you for your behalf. This is the section here that most amateurs would be using. If you need to calculate when the object, this particular object at this point, when it's going to reach your meridian transit. It'll reach your position in if you're going to be doing meridian transits across your north-south line. And this tells you the altitude and the azimuth at which you need to place your antenna. So in this case here, the antenna would be pointing 180 degrees toward the south, and you would have to elevate at 64.43 degrees above the Earth's horizon. And this is all based on the fact that this is the observatory location. In this case, it's my observatory, which is at 26 some degrees, but in latitude. So this is all calculated based on your location, which we've already learned you have to put in one of the setup commands. This gives us the time when this transition is going to occur today, And when the next transition a day from now, 24 hours later, or one sidereal day later, this is where it will be later on. So you notice we're updated here by about 4 some minutes, a little bit. It's the sidereal day, not the full 24-hour solar day. This gives you the current position. So right now, if you needed to point to this particular object in the sky, you would have to set your alti-azimuth positions correctly. And you notice that the hour angle here is toward the east. In any event, this is a handy tool that can be used to just calculate and set up and prepare to set up for scans and so on. If I do a calculate here, let's take a look and see what happens, just to show you that the time of transit here has changed a little bit because the Earth is still rotating. If I click it again, you see this 183 seconds. Let's find out again what it is. You notice now the time has changed a small amount because the Earth is continuing to rotate. This will just work until you finally reach your alti-azimuth position, and these are the settings you should already do if you're going to be doing meridian transits. These are the settings you're going to do if you're going to actually point to the object right now. And if your antenna is able to move east and west, then these are the values you'd be putting in. So that's pretty much it. These tools here are used for you, but the biggest point is that the heliocentric and Doppler corrections are very important in this program. So you're going to get very accurate data. You'll get the raw data for the combined measurement that you made, and then you can adjust it slightly by removing the effect of the Earth's rotation and heliocentric revolution about the sun. So I hope you enjoyed, and we'll talk more about other modes of operation when we get ready to talk more about the project scanning modes.